The way I look at vapor pressure is like this. So you have two phases here. One is a gas phase and the other is a liquid phase. So if we have a liquid here and we have an interface, so this interface separates the liquid portion, which is going to be here. I'll draw my little liquid molecules like this, and the gas version, which is above. Now, gas is going to be above this, but really right at the surface, that boundary between this liquid phase and the gas phase, can exist a vapor phase. So this vapor is actually very close to this interface that demarcates the liquid and the gas phase. And the vapor pressure basically is the pressure that's exerted at this interface. So it is a pressure. So we would expect units in atmospheres, millimeter of mercury, or torr. Those are the common units of pressure. Pascal is another unit of pressure. And in order for this liquid to exert a vapor pressure, what it must do, well, it must break free. So you're setting up a dynamic equilibrium between this water molecule here in its liquid phase and a water molecule here in the vapor phase. So we can have this back, forth going. And in order for this molecule to break free, quote unquote, and go as a vapor, that vapor could also come back down. And when it comes back down, that's when it exerts a vapor pressure. So this pressure that's exerted as it goes from the vapor state to the liquid state is the vapor pressure that's exerted by that vapor on this interface. So intermolecular forces that house the liquid that prevent it from going into the vapor state. So going from a liquid state to a vapor state or a gas state is evaporation. So that's competing. The vapor exerting a pressure in order to go back to the liquid state, and that is condensation. So two competing forces that are in equilibrium, condensation and evaporation. Now the question you have to ask yourself is, now what is preventing this from breaking free and exerting a vapor pressure? That is breaking free, going up, evaporating into the vapor phase, and then whatever goes up must come down so it can exert a vapor pressure on that interface. So the forces between these molecules have to be broken. They have to be dispersed in order for one molecule to break free in order to exert a vapor pressure back down. So if you remember from the previous lecture, we have our triangle, and or barrier, it has to be or must be overcome for this to become a vapor in order to exert a vapor pressure. So in that regard, hydrogen bonding and dipole-dipole interactions between two polar molecules are going to really affect the vapor pressure that is going to exist. Let's take a look at three liquids and determine their vapor pressure. All right, so here are three liquids, let's imagine. At the bottom is the liquid phase, at the top is air or the atmosphere, and we have water, carbon tetrachloride, and dimethyl ether. So water, in order for a vapor pressure to be exerted, remember the definition, okay? One molecule has to break free and evaporate, and the molecules nearby this surface then can exert a pressure, okay? Now, for this molecule of water to break free, what must it overcome? Well, if you remember, water has an extensive hydrogen bond, even in the liquid state. And a water molecule must overcome hydrogen bonds to other water molecules in order to break free, in order to evaporate. And then those molecules nearby acting at this interface, so the molecules acting at the interface can exert a vapor pressure. So we would expect the vapor pressure to be pretty high. So at 25 degrees C, now this vapor pressure really is a function of temperature. That's an important point to realize. As you increase the temperature, you're going to increase the motion of these molecules, and more will quote unquote break free. So at 25 degrees, water has a vapor pressure of 0.0313 atmospheres. So at this temperature, very little water breaks free to exert a pressure at that interface between the liquid phase and the gas phase. And probably because very little becomes a vapor, because it's very difficult to overcome that extensive hydrogen bonds. What about carbon tetrachloride? Well, carbon tetrachloride is a nonpolar molecule, and you're going to have nonpolar interactions. Not as strong, but still pretty significant. What do you imagine the per pressure of a completely nonpolar molecule such as carbon tetrachloride will be? And looking that up, we find that value to be 0.1513 atmospheres. So 25 degrees C carbon tetrachloride as a vapor will exert 0.1513 atmospheres. Okay, now at 25 degrees you have to quote a vapor pressure at a specific temperature. So here we have hydrogen bonding. Here we have nonpolar interaction or dispersion forces. And let's look at our final example here, dimethyl ether. We came across this in our lecture on intermolecular forces. These molecules are interacting with each other through polar interactions, polar interaction. This has a dipole moment that is partial negative, leaving these carbons as partial positive. And looking at the literature for the vapor pressure that's exerted at this interface, and these are polar forces, nonpolar interactions, polar interactions, dipole moments, shared across the molecules of dimethyl ether. So you can see here, just by looking at these values that are quoted at 25 degrees C, that dimethyl ether can easily break from its other partners, its other neighbors, and it could break free and in turn establish a dynamic equilibrium where it can return back to the liquid phase, and in doing so establish a vapor pressure of about 5.8 atmospheres at 25 degrees. Carbon tetrachloride can also do that. It can break free of those nonpolar interaction and establish a vapor pressure. Water with hydrogen bonding, it's very hard to disrupt that, and it's at room temperature. It's not going to exhibit much of a vapor pressure. So very little water exists as vapor at 25 degrees. As we stated, the vapor pressure is related to temperature. So a higher temperature, a greater vapor pressure gets exerted. A lower temperature, a lower vapor pressure gets exerted. So we can use the Clausius-Clapeyron Equation, which relates the vapor pressure of a substance to the temperature. And the equation is like this. So this is called the Clausius-Clapeyron Equation. And a lot of versions of these equations just go ahead and subtract 1 minus T2 minus 1 minus T1. That is, they get a common denominator so that you have one fraction instead of two fractions. So let's take a look at this example here. If you have pentane, which is a long chain alkane of 5 carbons, and at 1 atmosphere, is the pressure that it exerts, vapor pressure that it exerts at 36 degrees. And at 505 torr, it exerts, that is its vapor pressure at 25 degrees C. So what is the delta H of vaporization? So here we can just readily plug in chug, because we have P1 here, we have P2 here, we have T1 here, and then we have T2 here. The only thing that we need is the delta or the enthalpy of vaporization. Notice how your vapor pressure at these temperatures, so notice here that your pressure at temperature 1, your pressure at temperature 2 are related by your enthalpy of vaporization. So the enthalpy of vaporization, that energy, usually expressed in kilojoules per mole or joules per mole, it's per mole, sort of bridges the pressures and their temperatures. So let's go ahead and plug our values in. We have one pressure in atmospheres and the other pressure in torr. So we're going to have to change them. I'll change them to torr here. We know that 504 torr, there is 760 torr in 1 atmosphere, 664 atmospheres. And we have a common unit. Another thing we want to do is we want to change these to Kelvin, because the R, our universal gas constant that we use in the Clausius-Clapeyron equation, has a value of 8.314 joules per mole Kelvin. Because of that, we want to put our temperatures in kelvins to get the kelvins to cancel out. Now we have everything to solve. Atmospheres cancel. Usually the natural log does not have units. I do not know if that's taught in math, but natural logs, that number inside the bracket, does not have a unit. We can't take natural logs of a substance with units. If we do, we usually omit the units. We want to solve for delta H of vaporization, and our units here for R are 8.314 joules per mole Kelvin. And we do 1 over T2. Over T2 is 298 Kelvin. It's 1 over T1, which is 1 over 309 Kelvin. So looking at the units here, the kelvins cancel. This mole, the mole gets flipped. So having plugged in all our variables, we are ready to solve for delta H of vaporization. I rewrote the equation here. I went ahead and solved for this, put it on my calculator, and I got 0.000119 roughly. Kelvin stays in the denominator. And delta H vaporization is here. Is our value of R. We're going to use 8.4 joules per mole Kelvin. Take this 0.000119 and divide it by 8.314. The kelvins and kelvins should cancel out. Doing that, I'll get a value of 0.0000, that's 4 zeros, 143, and this is going to be in units. Now here I have joules over moles in the denominator. They get flipped, so that becomes moles over joules. All of that times your delta H of vaporization, or your enthalpy of vaporization. This is what we want to solve for. And that has to equal to the natural log of 1 over 0.664. Atmospheres cancel. So I'll go ahead and put that in our calculator. And in my calculator, I get 0.409 has to equal to the delta H of vaporization, enthalpy of vaporization of 0.0000143 moles over joules. I'm going to take 0.409 and divide it by 0.0000143 in terms of units. When I take this and divide it by the 0.0000143 moles over joules, by division the units flip and I get joules over mole, which is the unit that I expect for the enthalpy of vaporization. This in the denominator inverts and my units are going to be joules over mole, and my enthalpy of vaporization will now be 0.0409 divided by this number, 0.0000143 is my answer. A lot of times people will put the enthalpy of vaporization in kilojoules per mole. If the answer asks you, if the question poses to you to put the answer in kilojoules per mole, just divide this by 1,000. So 1, 2, 3. Move the decimal point 3 places and you'll get 28.6 kilojoules per mole. So when you go back to the Clausius-Clapeyron equation, you decrease the temperature from 36 degrees to 25 degrees. As a result, the vapor pressure exerted on that surface by pentane decreases from 1 atmosphere all the way to 0.664 atmosphere. If you look at the vapor pressure on the y-axis and the temperature on the x-axis, that is, if you graph this vapor pressure as a function of temperature, you'll see the graph actually looks like this. It has this curvature upward, and for different molecules, the vapor pressure will have a different dependency on temperature, but that direct relationship always exists. That is, as you increase the temperature, you are overcoming intermolecular forces, in this case the polar interactions of dimethyl ether, the hydrogen bondings of water, and the coordinations amongst the mercury atoms. And as you increase the temperature, the vapor pressure exerted actually increases because now more molecules are going into the vapor phase. So this is what the profile looks like for a vapor pressure versus temperature diagram. As an addendum to the Clausius-Clapeyron equation, notice that your delta H of vaporization, heat of vaporization, the energy usually in joules per mole or kilojoules per mole required to vaporize 1 mole of a substance, convert 1 mole of a liquid to 1 mole of vapor. That energy is related to the natural log of the vapor pressure. So this is a linear relationship, y equals mx plus b. In this case, the slope is sloping downward. And so if you plot the natural log of the vapor pressure, the natural log, at the y-axis and 1 over t in the x-axis, you get a straight line. And the slope of that straight line is minus delta H vaporization over R. So that's the relationship. This is a linear transform. You're taking this curve, plotting the natural log versus 1 over t. You get a straight linear relationship whose slope gives you the delta H vaporization divided by the gas constant R. Another thing is the vapor pressure at 1 atmosphere, where it hits, and at that temperature where the vapor pressure is at 1 atmosphere, that's usually the normal boiling point. So the normal boiling point of water in this example is at 100 degrees where it hits 1 atmosphere vapor pressure. At 357 degrees, that temperature, mercury exerts a atmospheric vapor pressure of 1 atmosphere, so the normal boiling point of mercury is 357 degrees C. And at 34.6 degrees C, diethyl ether exerts a vapor pressure of 1 atmosphere, so the normal boiling point of diethyl ether is 34.6 degrees. So normal boiling points is the temperature at which these substances exert a vapor pressure of 1 atmosphere, and at 1 atmosphere it's called a normal boiling point. We can do the same thing for the melting point, and that's called the normal melting